Thanks.
Okay.
Okay, welcome everyone to this Tunneling in QFT seminar. Today we have Karthik Rajeev talking to us about tunneling amplitudes in QFT. Karthik is a postdoc in Edinburgh. He started off life in Ayuka in Pune doing his PhD and has worked this whole maybe last 10 years or so on various aspects of tunneling, especially related to like Schwinger pair production and Hawking radiation and the real-time Lorentzian nature of tunneling. And yeah, so our first talk on Schwinger pair production in this series and something that's fairly central to tunneling in QFT. So very glad to have you here, Karthik. Next month we have on the 21st of May, Miguel van Vlasterleya, title yet to be confirmed. But yeah, when you're ready, Karthik, please take it away. Thanks.
Thank you, Ali, for the introduction and all the organizers for inviting me. Okay, so this the tunneling in my talk is not really tunneling in the configuration space of the field. It's more like the tunneling in the quantum mechanical sense, but adapted judiciously for QFT settings. So therefore, just to give an outline of why tunneling-like picture might emerge in QFT settings, particularly when you have particle production. Hawking radiation is sort of the one of the prototypical example of pair creation. So here I've given a Penrose diagram for a black hole which is dynamically formed by collapse of a null shell. So this green line at v equal to 0. Now v is a coordinate along scri minus or I minus, which is the asymptotic past for all null worldlines, massless worldlines. So this green line it basically represents the collapsing null shell. So towards the south of the south of this line, the space-time is just Minkowski, right? And you go north of the line, it's Schwarzschild. So it's a Schwarzschild and Minkowski stitched together in an appropriate way. And this the blue line is what will eventually become horizon when the black hole is formed. And of course, Hawking radiation is when you do QFT in this background, it's the spectrum of particles right around here. I hope you can see my cursor. So just the spectrum. Okay, thank you. So the spectrum in the asymptotic future inscribed plus is thermal, and that's the Hawking radiation. Now, so let's. My interest was one of my interests is to understand this from some of the tools used in particle physics, standard techniques, and how it can be adapted to examples of this kind. So, for instance, a particle physicist would think of, like a scattering amplitude in this background. So, for simplicity, let's look at scattering amplitude of a zero angular momentum massless scalar field state. So E is the initial energy and E prime is the final energy. So M is the amplitude and S is the S matrix. So this is what one would consider. But then to make more connection with the classical intuition around this background, for instance, if you are looking at the geodesics in this background, so there is clearly the sign of horizon is reflected in the kind of world lines or geodesics of the space time. For instance, if you look at this particular point V naught and look at the light ray that is going inward, so that's the the last light ray that escapes the collapse. So what I mean specifically is if you look at a null particle that is going inward slightly before this time v naught, so it goes in, and at some point it reaches the center. Sorry. Yeah, so at some point, sorry about the, yes, at some point it reaches the center where it becomes now an outgoing geodesic, and then it escapes to Scry plus. However, if you consider a light ray that goes in after v naught, so it goes in, it reaches the center, and it tries to go out, but then the black hole has already formed, so it can't reach Scry plus, but it goes into the singularity. Right? So this is, so therefore one is interested also in, let's say, wave wave shapes that are peaked at certain values of v, and then look at scattering, to make more connection with this intuition. So therefore, maybe an interesting object would be to look at this, which is m tilde, which is kind of a Fourier transform of this amplitude with respect to this coordinate v. Right? And since the energy is, of course, energy, it's positive. So this integral is along 0 to infinity for the energy. Consequently, this object m tilde as a function of v should be analytic in the upper half plane. Because if you inverse Fourier transform m tilde with respect to v, you should get a function which vanishes for negative energies. So this, so just because of the analyticity property of this function m tilde v, you expect that even for values of v, which is greater than v naught, this function is non-zero. So that's like tunneling, right? So you have a case where some wave function is non-vanishing even for even at places where it is classically forbidden. So this is, so yeah, we'll now later on we'll make this more precise. But just this is just to give you an impression that okay, this is one way of making sense of tunneling in QFT settings. So yeah, the overview is therefore to look at these tunneling wave functions describing particle production, for instance, Schwinger effect in strong field QED and Hawking radiation in gravitational settings, and possibly explore some of the similarities deeper using the worldline path integral formalism. Again, I'll stick to scalar QED for the Schwinger case and massless scalar for the Hawking radiation. Okay, so maybe just a brief introduction to Schwinger effect. So this is basically the decay of vacuum when there is a very strong electric field present. And so this vacuum decay happens by creation of pairs, and the number of pairs, the spectrum is given by this expression, and it is non-perturbative, non-analytic in the field strength, and so on. These are all well-known results. So the key takeaway from this slide is there is this exponential tunneling like factor that is of importance in this context. So here, there is an exponential factor which is precisely the number of pairs. If you look at Hawking radiation, of course, as I describe it as the black hole evaporation by pair creation. So there, if you look at the pair creation amplitude or pair creation probability when you square it, so it takes this exponential thermal like structure, and this capital M is the mass of the black hole, and epsilon is the energy of the particle produced. So again, you have this exponential form, which you might expect has something to do with tunneling amplitude. Okay, so so now we'll try to make this more precise by looking at these objects in more detail. So first start with, let's say, the Schwinger case. That is, you have a strong electric field. Let's briefly look at what happens in the classical physics scenario. So it is convenient to work in this light front gauge, where instead of t and x, you look at x plus and x minus, defined here as t plus or minus x. So these are called light front coordinates. And let's say we are interested in the particle or antiparticle solutions corresponding to some fixed momenta, p plus and p perp. So perp is the component perpendicular to the electric field. In this case, it is taken to be along x direction. So since nothing interesting happens along the perp direction, I'm just showing the minus component of the solution. So it takes this very simple form. Specifically, you can see that the function is bounded because of this exponential form, because the exponential function is, it takes values from basically 0 to infinity. So therefore, the coordinate of the particle takes an upper bound given by p plus by EE. So that upper bound is a function of the moment. So in picture, really what it means is these continuous curves are the solutions that I've written above. So if I plot it in the x plus x minus cross section, so you see that they asymptote to a certain line, and there are, for a given value of p plus, all of the solutions lie below this line. So in a sense, this is like the horizon, right? So, classical solutions for a specific value of momenta cannot cross a certain line in the x plus x minus plane. Yeah, so now the idea is to see what would be the tunneling-like solution. So basically wave functions which take non-zero values even in classically forbidden region. So which would be region which is north of this dashed line. Okay, so it's easy to find such solution. You can solve the Klein-Gordon equation and this constant electric field background, and you get the solution 1, which has all the tunneling behavior embedded in it. So for instance, you have this log function with a branch cut shown here with the I0 plus to show where the branch cut is oriented. Again, remember this is also related to the analyticity that I talked about earlier, but there it was analyticity in V, but here it is x minus. So in particular, the exponential factor that I showed earlier, it can be read off from the prefactor in the forbidden region divided by the allowed region. If you take the ratio, this exponential factor is precisely that relative factor. Okay, so therefore, in this sense, this exponential factor, which gives you the spectrum, etc., and Schwinger effect, is in fact the tunneling amplitude in corresponding to this wave function. Now, what I'm interested in now is to see how this tunneling factor emerges from a worldline perspective. That is, there is a conventional picture where if you have a tunneling, there is some complex path or world lines in complex time, etc. But is there a way to get it from real time Lorentzian path integrals? So, so the idea is to start with a path integral of this form for the wave function. So the wave function has an argument, and that argument is one of the boundary conditions in the path integral. And there is also the moment which is specified that will also be the boundary condition in this path integral. So you have the action, the path integral over Z, which is all familiar from standard quantum mechanics. But in addition, you have an integral over proper time t, right? So now, so that is in a sense imposing the on-shell condition. That is the condition that this is a particle of a certain mass n. To give a more quantum mechanical analog to this this extra this, which is the proper time integral, imagine trying to write a path integral expression for a fixed energy wave function in quantum mechanics. Right? So you would need some kind of a Lagrange multiplier to fix the energy, and this capital D is precisely that. But this time it is fixing the mass squared for the particle. For instance, if you look at this this path integral in the trivial free case, you will find that you end up getting this kind of an expression where the t dependence is just from a multiplication by this p square minus m square, and when you perform the t integral, you get exactly the Marshall as a delta function. Now, another thing to notice is that this exponential factor in here is nothing but the worldline action evaluated at the classical solution. And the on-shell condition in this case, p square minus m square going to 0, is equivalent to the saddle point condition for the worldline. So varying the worldline action with t and equating it to 0. So this will be important later on. Now let's do the same trick, same for the case where you have an electric field, and now working in a very convenient gauge, where the field strength, the gauge field is taken to be of this form. Again, the nice thing is that even here, you can the semi-classical computation turns out to be exact even here. So you have this semi-classical exponential. You also have a prefactor, which is new. We didn't have it in the free case. So, but essentially, the form survives. But of course, this worldline action, one has to be very careful what it means. So the worldline action is the semi-classical action here is evaluated in the worldline solutions given below. Now, these are not really the solutions that I showed earlier. Why? Because, as I was just explaining, the on-shell condition comes about only after integrating our capital T. So before integration, these are not yet the on-shell solution. These are some solutions which you get from the equations of motion, but you have not yet imposed the on-shellness condition. Specifically, I mean these solutions can, in principle, be time-like or space-like or anything. Right. And this final expression that you see here as an integral over t is therefore interpreted as a sum over several world lines, and these world lines can be space-like and time-like and so on. So from this perspective, the tunneling that happens in the tunneling-like phenomenon that happens in the wave function is because of the fact that there are these space-like worldlines that go into this path integral. Okay, so to specifically look at the classically allowed region, the saddle point of the worldline, denoted as TS, is the dashed line shown here. But as I said, there are several other worldlines that go into the path integral. And to get the wave function, of course, you can shift the proper time integral with to the saddle point and evaluate it. You get precisely the form that I showed earlier. But the interesting thing happens when you have you're in the classically forbidden region, and you would try to see what the saddle point for this case is, and it turns out that the saddle point is a complex quantity. And then you can do the same thing with this case, but this time you have a complex saddle point, and that complex saddle point gives rise to a complex worldline action, which in turn gives you the tunneling link factor. Now, this complex saddle point, if you translate it back into some worldline, it gives you a complex worldline. So that's a conventional picture where tunneling is interpreted in terms of complex classical solutions. But what I'm trying to say here is that is only when you do a saddle point approximation, but you could have equivalently said that this tunneling phenomenon happens because the path integral allows for space-like worldlines. So that would be the real-time or the Lorentzian viewpoint. And this complex saddle point is, in a sense, proxy to all these space-like worldlines that is going in. Okay, so this is just a warm-up of how to understand this phenomenon.
I think I understood, but can I just clarify?
Yeah, sure.
So in the case where you don't use the saddle point approximation, you're summing over only real world lines. They're just some of them are space-like and some of them are time-like, but they're all real.
Right. Exactly. Yeah.
Okay.
Yeah. And yeah, I mean, if you want to really look at or make a connection with the classical solutions of particles, you would have to assume or impose the on-shellness condition, which is, as I said, as I described earlier, it is basically the saddle point condition. But then what happens is that if you force to find an on-shell worldline in the classically forbidden region, then you get complex solutions. But you could have then you could have said, okay, this is just the path integral expression which allows for space-like worldlines, and that is equally good to describe tunneling. Anyway, so
thanks.
Yeah, thanks. Now coming back to Hawking radiation, so I'll just describe the standard approach. So it starts off with finding out the so-called out modes. So these are solutions which take the form of a positive energy vacuum wave functions near the future, that is chi plus. And then finding what that same function, how the same function behaves at chi minus. So basically tracing it back and see how what the functional form of it is at chi minus. So Hawking argued that for the late time modes, you can use geometrical optics to find the form of this function. And then once that function is found at chi minus, you can write them in terms of the Fourier modes, which gives the alpha and beta. So in particular, you will find that what was purely positive energy vacuum function in the future becomes a combination of positive and negative energy functions. So this beta is the proportionality constant describing, or the coefficient describing the negative energy component that has come about during the evolution backward, and that is that coefficient beta is what encodes particle production. But there is, from an amplitude perspective, there is probably a different set of boundary condition or wave functions. So these are what can be called as Feynman modes. Okay? So they have a bit of a different boundary conditions. So they are in the asymptotic past. They are purely positive, negative energy solutions, and these negative energy solutions are found from somewhat like a Fourier transform of the amplitudes. So you'll see that this is sort of resembling the initial slides that I had, which motivated tunneling. And then these same solutions in the asymptotic future becomes a combination of negative energy and positive energy components. And the pair creation amplitude, which I've denoted as M0 to 2, is encoded in the positive energy bit in the asymptotic future. Okay, so this is somewhat taking the out mode function based approach upside down. So the pair creation amplitude is now encoded in the future, which sort of makes sense if you ask me, right? Because it's particle production happens in the future. Okay, so let's, with this picture in mind, let's see how this is connected with tunneling. Now, Hawking radiation and tunneling is a long history. It dates back to, in fact, Hartle and Hawking themselves, and then several others. But before going into the tunneling bit, let me just take the tunneling as a semi-classical phenomenon. Therefore, let's start with classical first. So interestingly, there is just one simple object that you have to compute, which encodes all Hawking radiation information. It is the following object. So it's a change in energy, delta E, for a massless particle that starts off from some value V and reaches scribeless with a prescribed energy, let's say E prime. Okay. So how do I compute this? As I described earlier, so this space-time is basically stitched. It's constructed from stitching together Minkowski and Schwarzschild backgrounds. So therefore, energy is conserved independently in these two regions for this massless particle. So there is a conserved energy in the Schwarzschild region. There is a conserved energy in the Minkowski region. But the thing is that they differ. There's a difference. And it makes sense that difference comes from something to do with the light shell that is collapsing. And that is exactly what is given here. So you can compute the change in energy as the particle sort of crosses this shell from this form. So it's almost Newtonian mechanics, but this time instead of mass of the particles multiplied, it is the energy of these two particles. Energy of the particle, which is P, or moment of the particle P, and P tilde is the moment, the form moment of the black hole itself. Okay. So when you do that, you get this change in energy to be of this form. This is all that you require to compute Hawking radiation. So this is what I'm going to describe now. Now let's come back to this object M tilde, which we described earlier, which was this Fourier transform of the amplitude. Let's say, let's ask what this object would be semi-classically. So you would expect this M tilde to be some exponential of some worldline semi-classical action. But then you don't know the action. So how do we find the action? So for that, use the fact that you vary the action with respect to V, you should get the initial energy, right? And the initial energy is nothing but the final energy minus the change in energy. The change in energy we already computed earlier. And if you use that expression and just integrate over V, right? So because of this 1 by V and so on, you get a logarithmic function here. But the thing is that you obviously, those that expression makes sense only for massless world lines that escapes to infinity. But then you can use the analyticity argument to analytically continue that action into regions where it is forbidden. So equation 10 is after all that is done. So this I0 plus is taking care of the fact that this is an analytic function in the appropriate domain. So specifically, if you look at this action for region V greater than V naught, that is the classically forbidden region, because of this logarithm with the funny branch cut, you find that this world line action has an imaginary component. And the probability for pair creation is nothing but 2 times the exponential of 2 times the imaginary part of that world line action. So this is roughly how this is supposed to go. But let's maybe make this more precise. Maybe some of it was hand waving. We didn't really say what the path integral is and what the semi-classical evaluation of etc. So that is what we're going to come to next. Yeah, so as I just said earlier, there's a lot of history on Hawking radiation path integral based on path integrals. But here, what I'm trying to do is try to make this connection more, make this connect well with the amplitude-based approaches. That is, try to get amplitude directly, and also to make this Lorentzian approach more manifest here. Okay, so so now we are going to make this the hand wavy picture more precise. So let's say there is a tunneling wave function, or the Feynman mode that we described earlier, and try to see if there is a path integral description for it. It's all the same as what we did in the Schwinger effect case, that is in the constant electric field case. But this time, the world line action is the action for a massless particle in the sort of collapsing black hole space-time. So in that sense, it's also all the same. But now we need to be careful about what the boundary term or the boundary condition is that imposes the fact that this is this has prescribed energy E prime. So what I'm going to do is, instead of just presenting the boundary term as such, we just inspect what the boundary condition is to be in. So since we are sort of evaluating this, let's say evaluating the function at scribe minus, so the boundary condition for one of the points is that the coordinate value takes r tends to infinity and a prescribed value of e and some theta and phi, which are the angular variables. And on the other side, the final point of the world line, that's where you want to fix your energies and the fact that this is supposed to describe an outgoing solution. So then, so it turns out that the fact that you want an outgoing solution is given by this combination of v dot and r dot and so on being equated to 0. So that combination of terms imposes the outgoing condition. And the fixed energy condition is rather simple. It is just the fact that R dot is E prime. And since E prime is supposed to be positive, you want to impose a condition that R dot is a positive quantity, right? At this point, lambda 2. And zero angular momentum condition is nothing but the condition that the phi and theta is not changing. Okay. So it turns out that the funny combination of V dot and R dot can be written a simple way as just E dot equal to 0. Sorry, U dot equal to 0, where U is this function given in the square bracket in the last equation. Okay, so two important points. Despite all the functions and complications, the take-home message should be that the outgoing condition is that U dot is 0. It doesn't say U should be some fixed value. In fact, it can be complex. You only care about the fact that U dot is 0. And the other thing is that this R dot is supposed to be positive. These two things will be important as in the next few slides. Okay, so let's now do the geometrical optics approximation in this particular path integral. So there you get the semi-classical approximation as 1 by R being equal to exponential of the worldline action. Now this worldline action is not some hand-wavy argument, but you're going to evaluate it as literally the worldline action that of a massless particle in this space-time. But it turns out that since the worldline is null, the sort of the kinetic energy, the kinetic part, the standard worldline part of this action just vanishes, and the whole of the action is just the boundary term, and the boundary term is nothing but minus E prime U, right? So so the action is nothing but e to the power minus I E prime U. So this parallels the Hawkins ray tracing argument. Now what is left is just to compute this quantity U for V in the classical allowed region and forbidden region, so on. And as expected in the classically allowed region, you can evaluate this function U and you get this familiar form that we saw earlier. Interesting thing is the classically forbidden region, right? So by the same analyticity argument and so on, you would expect non-zero contribution there. But what we're interested in is to understand what are the word lines, what are the kind of word lines that give rise to such contributions. So just like in the Schwinger case, it was those space-like word lines. Here, I mean, these tunneling happens in a sense because we allow for word lines to cross the horizon and come back. I mean, there is in the whole path integral, nothing is forbidding the word lines to cross the horizon and come back. Right? So I've shown one of the example trajectory here. Now, what would be the semi-classical solution? Right? So, or what is the semi-classical solution that is relevant here? It turns out that the semi-classical solution, which in the Schwinger case was, by the way, a complex word line, which also was, as I was describing, was a proxy for all these space-like word lines describing tunneling. So here, all these wiggly word lines, which cross and come back from the horizon, they all the weight of such funny word lines are encoded in a surprisingly real geodesic. Okay, and that geodesic is what I've shown by the dashed line here. you'll notice something different here. So the geodesic sort of starts from the singularity and comes back to sky minus. That is not the case here, right? You start with V and you reach sky plus. It's going forward. But why is this? Why does it have to go back in time? So the reason is, I mean, if you had naively thought of solutions that starts from V for V greater than V naught and tried to evolve it forward, it would go inside and then reach the singularity like so, right? So, but you see that singularities are equal to 0, right? So if something is going towards r equal to 0 from a positive value, so r is decreasing. So your naive geodesic that starts from V and that goes straight into the singularity doesn't satisfy our boundary condition, which again, this is emphasizing, is that r dot should be positive. So your boundary condition sort of enforces that the worldline relevant for this region should be solutions that come backward. Because now, if it is coming backward from R, then it is the R dot is a positive quantity. Now, where is this all, this tunneling like things coming from? That comes from the fact that this the boundary term has a branch cut, and when world lines cross the horizon, the branch cut picks up non-trivial contribution. You see that although there are many similarities, there are some very subtle differences when looking at Hawking radiation and Schwinger effect. So it is just the branch cut or from the boundary term that this time gives you this exponential factor. But you see that this worldline itself is still real. You get the complex value for the worldline because the worldline itself crosses the horizon. Yeah. Okay. Now that this wave function is with us, let's make this make the connection with the Feynman mode functions that I described earlier. So remember, these are solutions which in the past have they encode one-to-one amplitude, but in the future they have this pair creation encoded attempt. So from basically the fact that okay, so first of all, there is this change in this in the asymptotic pass, you have this negative energy contribution, but the non-trivial part is in the positive energy contribution. So there is this this positive versus negative change happening in this Feynman modes when you go from asymptotic future and past. So it turns out that the fact that in the tunneling region, right, the world lines are they're supposed to travel back in time means that they are in fact describing not the particle wave function or contribution, but sort of the anti-particle contribution. So it is with that notion that traveling backward is the opposite sign of energy. You can sort of divide the contributions of the tunneling wave function, which we described earlier, and see that in fact this tunneling contribution, which is the exponential of 4 pi gm times E, matches precisely with the 0 to 2, which is a pair creation amplitude in the general form of the Feynman wave function. What I'm trying to say is that you can neatly write down the tunneling wave function we computed and match it with the expected form of the Feynman modes and read off the pair creation amplitude to be precisely this exponential factor. Yeah, so that finishes the section. So the summary is that in the Schwinger case, most of it was exact. We could do the path integral exact, evaluate the tunneling wave function exactly. And then we saw precisely that these space-like saddle points, space-like word lines give rise to tunneling, and the word line instantons or the complex word lines saddles, they're just a proxy of these space-like word lines. However, in the Hawking radiation, it is all a bit semi-classical, and the relevant wave function is in the Feynman modes. And what is open, at least to me, is to see really how these the the tunneling the geodesics that describe tunneling, can it be associated with some kind of other non-radial geodesics, etc. What I'm trying to say is that it's not very clear what the one-to-one connection is in here, because the complex, I mean, what would have been a complex geodesic is not really a complex in the Hawking radiation case. Yeah, what is again open is maybe to do this in more strict way using Picard-Lifshitz analysis, or to see how the T integral can be dealt with in more carefully. So those are something which I look forward to doing in the future. Yeah, thank you.
Thank you very much, Karthik. Yeah, very interesting talk. So we'll open up now to questions from the audience. Please either unmute yourself or raise your hand. Up to you in the audience if you have a question for Karthik. Let me just start with one while we wait. In this first picture, the Schwinger effect, you talked about how these space-like world lines are actually somehow what are being summed over and that give you the tunneling effect. But is there a way of identifying which space-like world lines are important?
Yeah, so although I haven't shown it in these slides, so in the paper we have sort of written down the directly the expression for amplitude in terms of word line path integrals, and instead of looking at the wave functions and reading off, etc. So then in the expression for amplitude, you can show exactly that these space-like word lines are sort of like let's see. So in constant electric field, the classical solutions are hyperbolas, right? These hyperbolic.
Yeah.
So the time like, so if you think of this two 45-degree lines, and then there is hyperbolas which asymptotes in a certain way. But there are space-like hyperbolas, the space-like cousins to these word lines, which start from future and end at future.
Yeah.
Yeah, it is. Yeah, so it is those kind of word lines that give rise to pair relation. So the nice thing about Schwinger effect is that you can show that this is in fact the case. You can show the exact word lines, and yeah.
Yeah, that's fun. The thing that I was thinking of on the contrary is the field theory case, like tunneling in a field theory, like where you have two minima and you can tunnel from this minimum to that minimum. We have this bounce solution, right, which is the complex saddle point.
Right.
And putting your analogy forward there, of course, there are field configurations which don't satisfy the equations of motion, which go from one minimum to the other minimum in a way that's not complex. They're perfectly real, but just doesn't satisfy the equations of motion. But which of those field configurations are important for the tunneling process of the real field configurations that don't satisfy the equations of motion? Yeah, I don't know.
Ah, okay.
But maybe it's more difficult in that case because there's more dimensions to play with.
Yeah, yeah, I would imagine. Yeah.
Any further questions from the audience? Right. If not, let's leave it there. Thank you very much again, Karthik.
Yeah.
And
Thank you so much.